So in this section 4.2, we're going to talk about precipitation reactions or metathesis reactions. So a precipitation reaction involves a couple of things. First, mix together two solutions. And when you do that, we get a precipitate, which is a fancy chemistry word for a solid. So this is just any solid. Now we tend to think of solids as like you're going to create salt grains in this experiment, but it's more like a fluffy mush that will come out in your reaction. So as we zoom in on this image here, it does get a little blurry, but we can see that this here looks kind of fluffy. And so it is often a fluffy precipitate that is formed. Now, if you're making salt, you can make salt in this way, and it just requires a couple of steps after that in order to get the salt grains that we know and use on our snacks. So we know that we can create a new solid, and it is called a precipitate. So we need to mix together ionic solutions. So an ionic solution, right? Ionic means created from a metal and a nonmetal. So these are compounds like sodium chloride or magnesium chloride or any other metal nonmetal complex. It could be made with a transition metal like iron chloride or barium chloride, or with something not chloride such as sodium iodide or potassium iodide, etc. So soluble means dissolves into its parts. So when it goes into water, if you pour salt into water, what you'll notice is that the salt dissolves. And so that is a soluble compound. Insoluble, we're going to say does not dissolve. And so I like to think of these as tiny rocks. So these are things that you should be able to visually see with your eyeballs. And so they do not dissolve into the components. And so those are the two things. For the purposes of Gen Chem, we tend to only have soluble or insoluble, or in Gen Chem 1. In Gen Chem 2, you'll study what it means for stuff to be partially soluble. So that's kind of like when you add sugar into sweet tea. We know it dissolves, kind of, but not always. And so an ionic compound, like we mentioned, is a metal, nonmetal compound. These are not nonmetal, nonmetal. That would be things like H2O or methane or sucrose, C6H12. That's glucose, O6. So ionic compounds. So chemistry is often considered a lot of pattern recognition. And so over time, scientists explored different options and they determined that all nitrate compounds were soluble. It doesn't really matter what the metal ion is. Sodium nitrate, potassium nitrate, barium nitrate, etc. But they also noted that most of the time if you have a carbonate, it is going to become insoluble. So what they did is over time they created this solubility table. So we can see that these two are always soluble, and that second ion is the acetate ion. So what the chloride section says here, which I'm going to highlight, is that if you mix chloride with any metal except silver, mercury 2, and lead 2, it's going to be soluble. Now this Hg2 subscript 2 superscript 2 plus is usually referred to as mercury 1 or mercury 2. Mercury 1, because each mercury has a 1 plus charge. We're not going to focus on mercury 1 a lot this semester. So we're going to just kind of see that he's here. we're mostly going to think about the silver and lead components. And so in this table, we do want to go ahead and memorize all of this. And the reason we want to do that is so that we can predict what our soluble or insoluble components are. So in this case, we want to determine if the following compounds are soluble. So in this case, if we think about sodium chloride, we can come back up here and say, okay, sodium or chloride. Okay, well, we know that that's going to be soluble. And I'd like to apologize for the moving back and forth, but let's consider the hydroxide. So hydroxides are insoluble except when mixed with ammonia and alkali metal cations, which is the first column, calcium, strontium, and barium. So that tells us that the barium is going to be soluble and the silver hydroxide will be insoluble. So silver bromide, an important exception. So this will be insoluble. So by memorizing the table, you'll be able to predict what they are. The other thing is with time, we'll learn that there are trends. So when we have two ionic solutions are mixed together and the metal ions switch anion partners, this is called a metathesis reaction. Now, we all know that I'm from Texas, and if you don't, we're about to find out. So when I was in school, we did a lot of do-si-dos. And so a do-si-do reaction or a do-si-do square dance event, at some point the caller yells out, now everybody switch your partner. So if we consider the AX to be red and this to be blue, what we see in a do-si-do reaction is that the anions are going to switch places. And so in this case, on the other side, we will have new partners for both A and B. So everybody was able to switch components. And so a metathesis reaction is about where we take two ionic compounds and switch partners. So for this reaction here, the magnesium nitrate plus sodium hydroxide. If we want to think about what the product is, we can think about what it is. So we know that in this case, the magnesium is going to interact with hydroxide and sodium nitrate. So we can then think about, we're going to have sodium nitrate plus magnesium hydroxide. So we do need to make sure our equation is balanced. It turns out we need a 2 here and a 2 here in order to balance the hydroxides and the nitrates and then the sodiums. So the trick is, what it's also asking is one of these going to be insoluble? So if you look at your your solubility table, which is the handout I gave you in class, all nitrates are soluble. So they're going to be AQ. Magnesium hydroxide, on the other hand, is going to be insoluble because this is not one of the exceptions. And so you would give this a state of solid because we are going to create a precipitate. So we can predict the products. So to write a metathesis reaction, it's more than just writing them out. And in the next several series, we're going to step through this in a little bit different way. So we can use the chemical formulas of the reactants to determine which ions are present, okay? We're going to write the formulas for the products. So we're going to create our do-si-do reaction. And we want to make sure that we write proper subscripts because that's really important. And then you check your solubility rules. And if either product is insoluble, you have a precipitate. And then you need to balance your equation. If both products are soluble, there is no reaction that occurs. So in this example, we are going to go ahead and step through all of the steps here. So our ions for barium chloride are Ba2 plus 2Cl minus plus K2 plus SO4 2 minus. This is incorrect. It should be 2K minus. So then we can go ahead and create new partners, and so the barium is now going to interact with the sulfate, and we're going to create potassium chloride. So we have KCl plus BaSO4. So the potassium chloride, when we check the table, we will determine is soluble, so AQ. And the barium sulfate is insoluble, so we will create this. Barium sulfate will be the precipitate. So we also want to think about how these interact with one another. So what about if we look at iron 3 nitrate and sodium carbonate? So we want to do the same thing. We have Fe3 plus 3 NO minus, NO3 minus, plus 2 Na plus CO3 2 minus. So our new components, we're going to create sodium nitrate and iron 3 carbonate. So when we mix these together, we're going to end up with sodium nitrate plus, in this case, we're going to look at the iron carbonate. And so this is, we need to consider our charges. So we will have Fe2CO3 3. So this equation is definitely not balanced. And so when we look at this, we need to become balanced. So in this case, if we put a 2 in front of the iron and a 3 in front of the sodium carbonate, that gives you 6 nitrates and 6 sodium. So if we put a 6 here, that will give us a balanced equation. And the states on all of these, yikes, are going to be aqueous. So again, we're just mixing we're taking one set of compounds and creating 2 new sets of compounds. So one of the things that we often want to consider as chemists is I only really care about the active participants. So an active participant, in this case, are the ions that create the solid. So if we think about this interaction of barium chloride and potassium sulfate, the spectating ions must be removed. And so the trick with spectating ions is that we have to kind of think about what it is that they do in this situation. So to write this, we would take barium chloride, goes to, plus K2SO4. And so we can think about this in terms of the ions that we're creating. We have a barium 2 plus Cl, 2Cl minus, plus 2K plus SO4 2 minus. Now what we learned earlier is that we're going to make 2 KCl plus barium sulfate solid. And this is aqueous. But aqueous tells us that instead we really just have 2K plus 2Cl minus. These are all in the aqueous state. So a net ionic equation removes anything that we see on both sides of the equation. So we can remove anything that we see on both sides. So if we were to rewrite this as a net ionic equation, we would get barium 2 plus aqueous plus sulfate 2 minus aqueous makes barium sulfate solid. This is a net ionic equation. So right now I've gone about kind of a little messy way about to get there. But the game plan is 3 steps. 1, write the balanced molecular equation. Now, in my opinion, we start with the products. Then, if we rewrite the ions to create the complete ionic equation, it helps us determine what the products are. So really, all of this is about moving together to figure this out. Okay, so this is going to be a little busy. I will do 2 of these, and you should attempt the 3rd. So first, we're going to talk about the mixture of lead nitrate and potassium iodide. So here's our starting material. So the first thing that we want to do is create or begin to create our complete ionic. So we have lead 2+, aqueous, plus 2 nitrates, aqueous, plus potassium, plus aqueous, plus I-, aqueous. And then we're going to go to our products. So our products in this case are going to be potassium nitrate plus PbI, in this case 2. And so to balance our equation, we need a 2 here and a 2 here. The trick is once we create a balanced chemical equation, we need to make sure that it's reflected here and here. So the question is, which of these, if either, is a precipitate? Potassium nitrate is a nitrate, so we know that that's aqueous. Lead iodide is, in fact, insoluble. So our products are going to actually start on the next line, because we'll just drag it over and then zoom back out. We have 2K plus aqueous plus 2NO3 minus aqueous plus PbI2 solid. So when we look at this, when we look at both sides of the equation, we can remove anything that is present on both sides. Once we do that, we can take our complete ionic and now look at just the net ionic equation, where we have Pb2 plus aqueous plus 2I minus aqueous goes to PbI2 solid. So that creates our, here is our molecular equation. We then have a complete ionic equation here in the box. And then in the circle is our net ionic equation. So these are actually quite simple when we think about them and we step through them. So we will do, I think we can do one more example. So we'll look at calcium, this first one up here, or I'm sorry, number 2. Write the net ionic equation for the precipitation reaction that occurs when calcium chloride and sodium carbonate are mixed. So you might have an inkling here that I did mention the polyatomic ions. If you haven't memorized them and you don't know how to name your samples, this is going to be a quite difficult concept because it will likely use their chemical names. So we have calcium chloride, CaCl2, aqueous, plus sodium carbonate, Na2CO3, aqueous. So in my opinion, the first thing that we do is we create the ions of these. So we have calcium 2 plus, aqueous, plus 2Cl minus, aqueous, plus 2Na plus, aqueous, plus CO3 2 minus, aqueous. So we can now create our do-si-do reaction where the sodium and chloride interacts. We have 2NaCl. Plus, in this case, we are going to make calcium carbonate, CaCO3. So sodium chloride is aqueous. The majority of carbonates are solids. Calcium carbonate is no different. So now we can complete our complete ionic with 2Na plus aqueous. Don't ever forget the states. 2Cl minus aqueous plus CaCO3 solid. So the complete ionic equation, to be honest, is very long. It almost always uses two lines. So we can cross out anything we see on both sides. So we see chlorine and sodium ions on both sides. So then we can rewrite our net ionic equation, which is our calcium 2 plus ion, aqueous, plus CO3 2 minus, aqueous, creates calcium carbonate solid. So there's a couple of hints or thoughts that I have. A complete ionics need 4 items on the left and 3 on the right. So what I mean is right here, we see 4 items here and 3 items here. So a lot of times students try to obliterate or break up their polyatomic ions into their many, many parts. Each of these ionic compounds should just break into a cation and an anion. And then your net ionic equation down here should only have 3 entities total. Don't forget to give this last one the net ionic equation for the precipitation reaction that occurs when solutions of silver nitrate and potassium phosphate are mixed. Give that a go and let's see what you get.